the Internet of Things Industry 4.0 class. My name is Lucas, and I'm going to talk a little bit about my sensor that I've chosen for this seminar, which is called the GPS or Global Positioning System. I've chosen this particular sensor because I like an active sensor that also has some very challenging problems, because everyone knows that the bigger the problem, the bigger the check, and it makes it a little bit more fun to study. So here we are. GPS, you can, for example, use it to measure this bridge, the distance of the bridge, or where this bridge is even located and where it goes. And of course, GPS are used all around the planet and even in space. Neil deGrasse Tyson once said, space in general gave us GPS. That's not specifically NASA, but it's investments in space. And he's a very, very prominent figure in his scientist field of space. And GPS, the origin story, it actually comes from the Sputnik era, when everyone was racing to go to the moon and into space. And they realized shifts in its radio signals called as the Doppler effect. And it's a little bit like this, is when you stand over here and you hear an ambulance coming from the street mile away, and then when it comes closer to you, it becomes more intense. And as it passes you, it becomes fading away again. And depending on this, we can actually measure, remember, sound waves are exactly like radio waves. That's right, that's just waves. So you can measure the distance between the waves, the oscillating differences here between the waves, and you can actually measure that as a distance using the Doppler effect. However, one Doppler effect isn't enough. You need a couple or even 3 or even more points of contact, because as you can see, satellite number 1 here only has 1 ring of Doppler effect. However, if we put 2 satellites here, it will become a small ring in the middle. And as we have 3, we then notice that this satellite in the middle, which we are trying to locate, are in the middle of these 3 satellites in the middle point here. So tri, meaning 3, multi, more than 3, so that is if we have more than 3 satellites, that's multi. Then lateration is the distance between, and the angles, angulation, which is the angles. So explanation is very simple. It's basically like this. Distance equals speed times travel time. So in this case, distance might be kilometers, speed is the speed of light normally, and then you have the travel time, which is basically usually milliseconds. So we can use this formula to understand where something is, how far it is from one point. And then depending on the different points together, we can understand where things are. The satellites themselves, receiving or sending, use pseudocode. So they transmit their own pseudocodes. And depending on how that pseudocode looks like, pseudocodes meaning a simple language for the machines to use and produce, we can actually see how far away they are from each other. So this is a perfect example of that. You have this satellite code signal, which is the upper one here. And you can see it has the same pattern, okay? However, the pattern, when it strikes at the specific point, you will see a special lag. For example, this should be here, right? So this one right here is a little bit after. Depending on how fast in between, like this one, or how far behind it is, that is the distance. Because remember, as we said, the distance equals travel time and the speed of which the radio signals travel. So here we have the formula. So how do we use this practically? We need to use it for all the satellites. So sensor 1, the satellite number 1, if it's on its own, it only has its own relative position. However, if we bring in another sensor, another satellite, now they can communicate. And we can see that in between here, we can find an area where it can locate things. However, we don't know exactly where in this area something is. But we bring in a third sensor, we can now calculate 2 points. And it's not until we bring in a 4th sensor that we can see a specific point and not just a line in between 2 points. And now we have a position, a GPS location position. So the region gets smaller. In real use, if you've ever heard of Starlink, they are based from Elon Musk's satellites. The Starlink system is basically satellites going around the planet giving people internet connection. However, if you want to see one of these satellites, you can. So this one right now is above somewhere in Africa. And if you would be right here relative to the satellite's position, which is moving very fast, by the way, you would actually see the satellites if you look really hard. So this is updated every second and communicates with other satellites to find its position. Now, where can you use these GPS applications? For example, in agriculture, you will use it for planting, where to plant, where to put more water for your plants, fertilization, GPS-guided tractors and drones to automate work, to save time and have more efficiency. Space exploration as well. Of course, if you have very, very big items in space that don't that you don't want to collide with each other, it might be good to know their position, so you don't waste maybe $1 billion worth of projects. And then you have surveying and geodesy, which is very, very important for people constructing things, to survey the lands and so forth. Other fields could be infrastructure monitoring. For example, this bridge here, you can put GPS positions on this and accurately see if they move to assess potential risks or damage to this bridge. Military and defense, see where a boat is, or maybe navigate a missile, for example. Oil and gas exploration, knowing where to drill for gas, for example. Now, I've chosen as an actual sensor that is called the Shadow Tracker, Complete GPS Tracking System. It does use a GSM system and not really the satellites always, so we can use the antennas as well with the mobile phone system. And you can basically put it anywhere, and with a PC you can find out where it is. So let's check the data sheets for this device. And as we can see, it has a C/A code, pseudocode that it follows, which is a coarse acquisition code. It works on the frequencies of 1575.42 megahertz on an L1 radio frequency. And it can get the position up to 10 meters, 5 meters if it uses WAAS. And some general stuff to know: dynamic conditions, altitude up to 1,800 meters in the air, and then it maybe lose connection and so forth. TTFF, time to first fix, is how long it will take until it actually updates and gives you a location point. Here we have some other stuff: GSM, air interface, for example, the radio link between the mobile station and the base receiver station. And it will use 900, 1800, or 1900 megahertz for the tri-band. Class 4 and Class 1, it will use slightly different modulation. And then GRPS, what this means is basically a general packet radio service, so it uses terrestrial towers instead of satellites, which is cheaper. Class 12 means time slots is 4 up, maximum of 4 down, and have a maximum capacity of 5 at the same time. So type 1 also means that it cannot transmit and receive at the same time. And channels 1 to 4 are the radio blocks, the radio blocks, the modulations allowed, for example, and explains also the bitrate hysteresis or deviation or overhead. So here we can also see the dimensions of the actual sensor, what you can expect from it when it's operating up or down, with battery, without battery, and so forth. And here's more interesting stuff, because we can assume it uses 4.2 voltage like it says. We can also assume that it has a 270 milliamps current with a resistance of 15.5 ohms and a power of 1.134 volts. However, how long will actually the battery last? So I went ahead and calculated this because it's very interesting for me that we have a capacity of 750 milliamps and the charging time is 3 hours. So I was thinking, if it takes 3 hours to recharge this thing, then how long can I use it for? And it turns out that I can use it for 2 hours and 46 minutes if I'm in operating mode, which is using the device, pressing the buttons and so forth. However, if I have it on standby, which still tracing, I can have it for almost 6 hours. So I can trace something for 6 hours onto an end before the battery dies. Now, what secure systems are we using? We are using anything from the Russian GLONASS, Galileo system, or the China Beidou system, apart from the USA system. However, all of these systems actually, they're not really available for 100% accuracy and precision, and they're also quite jammable. And the reason for it is because it's degraded a bit, so military or the governments can have a slightly better system with more precision and more jam resistance. So when you're walking around with your mobile phone, you go to different parts of the world, you will actually use different GPS satellites and systems. So how hard could it be to fix up? It's only a couple transmitters and receivers, but really, why are these systems so expensive to maintain? First thing is the connectivity. As you can imagine, the radio signals can be distracted. Like, think about it, walking around in your house and you walk to the back end of the house and you lose complete connection talking to your friend on the phone. And the reason for this is because radio signals are quite sensitive. They will be blocked easily. And especially important is if you're uploading something or you're trying to change something in the system or trying to calibrate something, then even a slight blockage of your radio signals can be huge trouble. So imagine if you have frequent updates to do. And also, after that, if your device that you need to change moves a lot, for example, it's a satellite moving very rapidly in space, or it's an airplane moving very fast through the air, it can be challenging. And then, on top of that, software and firmware updates. For example, technology always improves. However, The satellites that are still used to this very day for GPS is quite old, and the hardware for these are quite limited. So you always need very, very intuitive and new ways to work around the new demands of technology, because sending up satellites are not very inexpensive. It's quite expensive and very complex. And then you have differential GPS, which are required for example, when you need exact precision, agriculture, and this as well need some reference stations to correct the GPS signals, and it's just very complex systems. And then you have real-time kinetic GPS, which needs a base station and then has a rover receiver that sends back to the same base with the satellites engaged as well. And so these ones all have their set of different systems that all together needs to be connected at all times, which is quite difficult. And so what could you earn if you work in this field? If you're an electrical electronics engineer and you maintain these kind of sensors, you can earn up to 65,000 to 150,000 or more per year. If you're a geospatial or surveying profession, then you can earn up to 50,000 or up to 120,000 or more. And if you're an engineer with automation and control, then you are earning somewhere between 60,000 to 140,000 or more per year. So it's quite expensive salaries for someone just changing out a light bulb. But remember, it's not just a sensor. It needs to always stay connected, calibrated into its relative position, even in space-time and gravity and so forth. So it's very, very, very complex, and that's why I chose this type of sensor, and I hope you enjoyed it, and you enjoyed listening to it, and hope you learned something. So until next time, thank you very much.